and it will end. So this today is the last lecture about the canonical. So last previous lecture, we talked about the partition function for n particles when the system is fixed at a fixed temperature. We call it this system canonical and some. So we show that in the different case when the particle is non-localized, so you have this expression for the partition function, and when the particle is localized, so you don't need it to have this factorial here. So, and Q1 was a single particle partition function, so it was sigma R E minus beta E R. So everything depends that if you have the energy level of the system. That's very difficult. That's very difficult to find the energy level for any system because many of the system doesn't have the exact analytical expression for the energy. What you will do with that, for example, nonlinear harmonic oscillator. You know that the simple harmonic oscillator has the energy level of n plus 1 over 2h bar omega, for example. But if you have nonlinear, so nonlinear harmonic oscillator, what you do? Oscillator. I mean, in this case, the Hamiltonian is given like the Hamiltonian of the simple harmonic oscillator plus the nonlinear terms from cubic terms of energy. What you will do with that? There is no any exact solution for that, and there is no any exact solution for the energy, so you cannot find the energy. When you cannot find, what you will do with the partition function, how you want to handle the partition function. So first reason which I want to deliver this lecture is that I want to talk about the case which you are not able to find the energy level, one. Second is that some systems are basically classically. So what you will do for classical systems? So some systems are considering the classical limits. There is no need for them to consider quantum mechanics. So what you will do with these systems? So in classical system, you don't have any quantization. You have just the Hamiltonian as a function of the h, as a function of the p and the q, yes? And this defined in the phase space. So what you will do with that? What you learned before that, for the classical systems, you can use the microcanonical ensemble. We get the idea that the number of the accessible state was a function of n, e, and v was proportional to the volume of phase space. Before we talked about that. So was integral of d to n q if there is a three direction, and the Hamiltonian should constrain between the range of e minus delta over 2 and e plus delta. This is what we did in last lecture for microcanonical. For microcanonical, that was the correct. By microcanonical, you have just one. The system is defined by its energy, so energy is the parameter for microcanonical. But here we fixed the temperature. So today I want to talk about the extension of this integral when you have the canonical answer. And you remember that here the density of the particle in the phase space, consider it as a constant, You remember constant and zero. Constant if h is in this bond, so e minus delta over 2, e plus delta over 2, and elsewhere, any other way, or any other place, we consider rho 0. And based on that, you did your calculation like partition theorems and these things. So I want to do this. I want to focus on the generalization of the concept of the volume of the phase space as a density of the accessible states in canonical ensemble. It becomes more and more technical. So we are passing from the elementary physics to the advanced physics. So I don't want to back again and explain about, so far still in the canonical we have this, so this is, the problem is that how to define Q1 when you want to work in the phase program. No, this is the only problem we need to handle. So Q1 and the partition function single particle partition function is, okay, it should be something like the volume, huh? But the problem is that here, each energy state has a probability. The probability is the Gibbs factor, E minus beta H ER. This is the weight actually. The weight of H or any energy state, and if you consider this over the total, it gives you the probability. So we talked about that before. So what is the analog of this in the phase space? Analog. How I can copy this weight to the phase space? This is called energy representation in quantum mechanics. So energy representation, you are working with energy level. I want you to give me the idea of how to translate this expression to the phase space. So you don't need to think too much. Translation of the eigenvalue of the Hamiltonian to the phase program is just Hamiltonian. Instead of that, you can put H, Q as the P. Of course, this vector is 3-dimensional. Q1, Q2, Q2. I write this. And what I do for this, so this is the trace. I told you, this is the trace or the summation of the matrix element, diagonal matrix element. So what I can do with the trace for the phase space? So trace will be like just integral over the whole space. So if I I told you, I prefer sometimes this notation. I write all the notation for you because this is the problem for many people, so they are a bit confused at that. When they open the book, so they are not followed, they cannot follow it. I write all the notation which I ever see in my life. So even they, I told you, they call it the Z sometimes. This is more popular in quantum field theory. This is more popular, I don't know where, maybe in chemical physics or something. They use Q1. So is it complete? No, that's not complete because you remember about the uncertainty principle and the idea of that the phase space has the minimum area. So there is no any minimum area. I mean, this integral has dimension. See, volume. It needs something to make it dimensionless because the partition function doesn't have any dimension. You see that here. What is the dimension of partition function? Meter, kilogram, joule. What is this? Q. Nothing. Exponential of number, so it's numberless. So this should be made as a useless. Always I need to check that this is a 3NO. Okay, now I promise you that will leave the partition function for one particle, not single particle. So you don't need to write N because I write for the single particle. For N particle, you just need this, make it the power of that.
Dr. H stands for what? H stands for what?
H standing for to make it this dimensionless, like the original one. And this is the one reason. The second reason is that you needed to divide this by the volume. You need to divide that to the unit. So this is the unit of the phase portion. H cubic is actually integral of dq dp. Yes? Uncertainty principle is in the order of the H. It's not equal to H. This is an order because we are talking about statistical physics. So this is the partition function for single particle. That's all. And there is nothing here new, so after that you can just find the partition function for n particle. It depends to your Hamiltonian. If your Hamiltonian has a potential, so you are localized at particle, you need to use this equation. If your Hamiltonian doesn't have any potential, so it means that your particle is non-localized. So you need to pass to this. I want to solve one example for you here to see that how these equations work. But remember that, you should not forget that this expression for the partition function or the other one which I write in terms of the energy level, should be same. I mean, for harmonic oscillator, for example, you know already what is the energy level, n plus 1, n plus half, h bar omega. So you can use that definition. But already I know what is the Hamiltonian for simple harmonic oscillator, so I can use this. I mean that the results will be the same. I don't need it to check that, but I will do a classical calculation and you can check it the quantum calculation and you see that everything is, what is the everything is the same. I mean, for example, Helmholtz energy will be the same, entropy will be the same, the total energy will be the same, these things. The macroscopic quantity will remain the same, almost. So the example which I want to talk, because after this example I want to pass to the important concept of the energy fluctuation in the canonical ensemble, and that will be the all. So we almost peacefully finish this canonical. The example is what example we want to solve it. We can solve the normal classical particle, or either we can solve it the harmonic oscillator. I prefer the simple harmonic oscillator. So we have an n simple harmonic oscillator, and consider that in the classical limit, I mean classical form. So I mean, I don't want to, for example, I don't know the energy level, or in case I want to consider the system only in the phase space. So see, this is not real. So doing the calculation in phase space is wrong. Conceptually is wrong, because there is no any classical statistical physics. You understand? All the statistical physics is quantum mechanical. Because when you have more than one particle, and then you have the potential, and when the size is tiny, so this is the regime of the statistical physics and quantum mechanics. But we use the concept of the phase portrait just to make the simplification for our calculations. Or sometimes the systems are really classical. They are really classical, like the gas in this room, for example. There is no such quantum feeling about here, because temperature is high, 27 degrees centigrade, for example. In this temperature, you can ignore about the quantum effect. Sometimes this quantum effect really not important, and sometimes we just use this, so we can use that, and sometimes we use this equation just to make the simplification for our calculations. This is the one of them. We use that just to make it, to reduce the level of calculation, or I don't know, just to get some handy calculations. So Hamiltonian for this particle, for one single particle, is that Ps square over 2m plus, So you have a potential here, so the potential say that the particle is localized. So you need to use this equation. So Q n beta will be Q1 beta and factorial. And what is the Q1 beta? Q1 beta will be 1 over h3 integral exponential minus beta p square over 2m minus beta m omega square over 2q square dp dq. Okay, so this is a q1. To do this integral, this is the one of the integral which we are lucky to make analytical expression easily in the lecture. So p square is px square, py square, pz square. So I can write this integral, look at me how I will write. I will write this integral like that. Multiply to okay. You know that we have a three coordinate and the system is isotropic. I mean the momentum in the x direction, you can make the integral the same as y and z. So each integral is very easy to calculate. We have the Poisson integral, so this is the Poisson integral. So radical p over a is the Poisson integral. So that will be radical 2mp over beta, and this is will be radical 2p beta m omega square. So 1 over h 2mp beta multiply 2p beta m omega square 1 over 2 cubic. Let's to make it more simplified, so I can write it 2 pi is out, so 2p h beta omega, and I want to write this like h bar beta omega minus 3. H over 2p is the Dirac constant. You can't imagine how many people they don't know the name of h bar. You can't imagine. They call it this Planck constant. When you ask what is this Planck constant, why did they put it this? So, you can't imagine. So this is the single particle partition function. So immediately I can use these results and define the n particle partition functions. And it's very interesting that this partition function, am I right? Yeah, everything is fine, yes. Okay, so just using this, so Qn beta will be just Q1, and we did a mistake because we write localized, but we write the equation for non-localized. Localized. So Qn will be beta h bar omega minus 3n. And immediately after that, you write the expression of the beta ln Qn, Helmholtz energy, so minus 1 beta ln beta h bar omega minus 3n, so 3n over beta logarithm beta h bar omega. This is the partition function, and this is the Helmholtz energy for the simple harmonic oscillator, three-dimensional simple harmonic oscillator. When you have A, you can calculate many things, like you can calculate the entropy. I think in the last lecture I write one of the equations incorrectly, so you need to pass and correct that equation. The entropy is minus 1 the A on the T, but I think when I watch my YouTube, I find I write it better here. No, this is the T. If you want to convert that to the beta, you need to change the variable. So, like here. So this is the equation. So from this A, you can find entropy, but you have a little difficulty because this integral is written in terms of the T, but here you have a beta. So yeah, this YouTube at least is useful for us in sense that we can review our lecture and find if there is a mistake, because we are not even the Albert Einstein accepted his mistake, you know. And some of us are very much afraid to accept, but no, I say that last lecture I did this equation wrong. So what happened? Nothing happened. Why we are so afraid, some of us? So let me to calculate the entropy because it is useful. So entropy is minus partial A on the T. One thing I censor, so I passed from one concept. Do you know what I didn't talk about here? One quantity I never talk about here, even I never speak about that, the pressure. Pressure is change in the system when you have the change in the volume, huh? But where is the V here? Do you have any V here? No.